Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's see. So this talk came out of some thinking I had. I wanted to trace back the last 10-15 years where I've been involved with a lot of optimization problems. I just wanted to put all of them on a sheet of paper and then see what are the relationships between various methods. And in the process I said, yeah, there seems to be some nice trends and happenings over the years, but essentially involving the same class of methods, but then different instantiations of those methods. I thought it will be interesting to present them as a historical view. So that's how this talk started. And actually I'm doing this talk, I gave a very preliminary version of this at a different place. I'll mention about that as I go along. So this is a tutorial, so I've deliberately made things as simple as possible so that try to convey the main ideas rather than going into details of methods and so on. Okay. So first about this talk, some warnings. The aim is to give a historical view, and I'm not really attempting to cover all possible good methods and then cover them in detail, not even mention them, right? So don't be offended if one of the methods that you publish doesn't appear here. It doesn't mean that I look at them as bad. It is just that they fit into this historical view, but then I wanted to choose one generic method and then talk about it rather than talk about all possible methods there, right? So I thought these methods fell into a few groups, and in each group, if you look at the class of methods, of course there are differences, but then there is a central computational theme in each one of those groups, and within them I just picked one method, and I didn't pick the best method. Instead I picked the simplest method that I can easily explain, right? And it turns out that all these simple methods which I choose as candidates from these groups, they solve the nearest point problem, which I'll explain in just a moment. The geometry is so simple and easy to see, and therefore I can just keep conveying the ideas very quickly and moving along, right? So what are those? So first a few notations. What happened? Okay, so you start with the feature vector x, which is sitting in real space of dimension f. So that's the base. F is the number of base features. Okay. And then you may want to transform your base features into a transform set of features, and that I use capital F. And F could be infinity. For example, if you use RBF kernel, you go into an infinite dimensional space. Then I have another space, which is the actual space where the optimization problem will be cast, and the dimension of that space I'll call it as D. Okay, so I just want you to remember the small f, capital F, and the D as we go along. So I'm going to use support vector machines as the main example, just binary classification, but then many of the things that I'll be talking about, the ideas also apply to the other extensions like multi-class and even structured output methods and so on, right? Although some of the issues could be very different there. So you have a training set with input outputs xi, yi, n examples. N is the number of examples, right? And that is also part of the notations. In fact, I should have mentioned it in the previous slide, but we should remember that n is the number of examples. And so you have the standard, the training optimization problem. And I've written a general loss function here, L of xi I, and the output is product of W and the transform features. And this loss function, one could take hinge loss or squared hinge loss or any other loss, but I'm going to focus on the hinge loss, on the squared hinge loss. If you take the squared hinge loss, that non-negativity constraint is redundant, so you can just throw it away. And hinge loss I will not be touching because this one is much simpler to look at. Right? And for this, yes?
I have a request. I can't see any of the slides. Would it be possible for you to read out whatever the equations is?
Oh, equations. Okay. So the first equation I mentioned was the standard training objective, which is half norm W squared plus summation over I over all the examples of a loss function L, and that L could be a hinge loss or a squared hinge loss or anything else. And I was just saying that the loss that I'm going to be looking at in this talk is the squared hinge loss. Okay. And the nice thing about squared hinge loss is that you can do a transformation on the weight vector W by bringing in, see, you have the half norm W squared term and then the hinge loss term, which is again a sum of squares, right? It's a xi square term, right? And therefore everything looks as squares, and therefore by bringing those psi I elements together with the W elements and putting them in a big vector, you can write the whole thing in a single quadratic function. That's what I've tried to do here. So I extend W with all these loss terms xi I and put them all together into a vector W tilde. And similarly, I take on the feature side, I take yi times phi of xi, and then also put an appropriate 1 over root c kind of term there. And then when I pad out all these things, then in the transform space W tilde, the optimization problem looks nice and simple, right? It's trying to minimize half norm W tilde square subject to inequality constraint Z transpose W tilde greater than or equal to a vector of ones. Okay, it's a nice form which is easier to handle, so that the rest of the talk I just have to look at this problem. Okay, and so the Z, which is the coefficient matrix that comes in the inequalities, it has columns, the small zi, okay, which are basically the zi's which I have written here. They are basically derived from the original examples, the transformed examples, right? And so those form the columns of this matrix Z, right? And if you evaluate, take two of the Zi and Zj's, do an inner product, and you can calculate a nice form, which is, it's a nice, kernel form that you get. Okay.
One more thing, if you don't
Yes.
Do you want to take questions and discussions now, or you want to reserve them for later?
You can ask questions anytime.
So regarding this formulation, I agree the optimization is much easier.
Right.
But if you actually look at the dual, then you find out the only points that will be support vectors are based on things that are misclassified. So this might actually be a lot less robust than the hinge loss.
Right. So one comment I want to make about that, Manik, is that I don't want to bring in any issues of performance, whether this model is better than the other model, none of that in this talk. So this talk is purely about optimization and complexity issues. Okay, so you are right, perfectly. For example, one of the drawbacks of this squared hinge loss is that the number of support vectors tend to be extremely large compared to like hinge loss, right? Which is a negative thing. But I'm not going to be, interested in any of those issues here, right? It's only about optimization methods and the complexity, how fast you can solve things. And so in this case, you recall our notations. So the transformed feature space has this F, right? So the optimization problem here, if you look at it, which involves the variables is W tilde, that will have F, capital F, if it is hard margin, capital F plus N if it is hard margin, because you're padding it with some other things, right? Okay, that's just a note. We'll come back to this. Now I want to talk about primal and dual. So this problem that we have formulated is the primal problem. It's here, and then you write the standard Wolfe dual for it, right? Which most people are familiar with, which you can compactly write as min half. I put the half at the wrong place. So there's an error here. So min E transpose alpha minus, there's again an error here, so it has to be max, sorry. So it has to be max of E transpose alpha minus half norm Z alpha square, right? Subject to alpha being non-negative, right? That's standard Wolfe dual. And I prefer to operate in a slightly different format, which is minimize half norm Z beta square subject to E transpose beta equal to 1 and beta non-negative. So it's another set of variables. So it turns out that this problem is also equivalent to this. All these three are equivalent in the sense this is a primal and these two are both duals. These two are actually equivalent, and this is the equation that connects them. So beta is equal to basically a normalized version of alpha becomes your beta. Okay, so why do I show interest in this problem? Because it turns out that it is a nearest point problem. So in other words, this problem you can actually very easily see that it's equivalent to this problem, which is basically, if you look at it, what you're doing here by Z beta is you're taking a convex combination of the columns of Z. Right? So you're forming convex combination of a bunch of points and trying to minimize that norm. That's what you're trying to do. So I basically rewritten this as this form. That's it, right? And so that is a well-known problem called the nearest point problem. And there are various methods for solving it. Like going back to 60s or even earlier, there have been methods for doing this. One of the earliest methods is what is called the Gilbert's method. And so now here is where I group these methods. So I started with squared hinge laws, and that led me to the nearest point problem, for which I'm using this method called Gilbert's method. But if I started with some other laws and tried some other method which is sort of very similar to Gilbert's method in principle, then you have these methods, right? So you have what is called SMO, sequential minimal optimization, SVM light, successive over relaxation, a dual coordinate descent. I put stochastic gradient here because it has some close relations. I'll mention this bit later. I put slightly shaded because it really doesn't fit in with these methods, because stochastic gradient actually it's a primal method, whereas these are all dual methods. But still, when you look at the basic format of the computations, it has a lot of similarities. And that's why I put it in this class. So this is one class, and then the next is a series matrix based dual method. So I basically take the same nearest point problem and I can use different class of methods, and an example of that method is what is called the Wolfe's method. Like Wolfe keeps coming everywhere. He's a very well known optimization person. In fact, later I'll mention that some of the things he had talked about. He didn't say large margin, but he did a large margin formulation back in the 70s at IBM when he was solving pattern recognition problems. And then there's a method called Kaufman's method, chunking, and all that. It could be, I missed many others, so I just put etc. So all these methods fill into these matrix based dual methods. And then I want to talk about primal gradient methods, also third class. An example of that is this finite Newton method. Again, it's a very easy to understand method. Then Chappell's primal method, bundle method. Bundle method is very different, but it fits into this class in terms of the properties of the computations. Nonlinear conjugate gradient, all these fit into this third class, right? So I'm going to basically take these three classes of methods, take Gilbert's method, Wolfe's method, and the finite Newton method as the examples, and do that in the rest of the talk. And Elmer Gilbert was my PhD advisor. That's why, right from day one, when I went under him, I've been sort of working with nearest point method. So it's, that's another reason why I like to present everything in terms of nearest point methods. Again, another thing I want to mention, which I mentioned earlier, which is that a preliminary version of this talk I gave there was a workshop in Professor Gilbert's honor about 2 years ago, and I wanted to give him a good feeling, and I said, hey, Gilbert's method has a serious role in machine learning. So this talk was basically used to convey that, and of course he felt very happy about it. Let's start with Gilbert's method, right? It's, as I said, it's all geometric, very easy to understand. So you're given a convex set. I've drawn it in a smooth form, but it is actually, as I said earlier, the nearest point problem is you have a bunch of finite points and you form a convex hull. So it's really a polytope. But then, just for this, sake of ease, the fact that the method is applicable to general convex sets, I just drew a general convex set. So you're trying to find, you're given the origin, you're given a convex set, and you're trying to find the point on that convex set closest to the origin. That is the problem, right? And let's see what one iteration does. We'll understand what Gilbert's method is. So you start from a point, then join the origin to the point, right? And then think of the negative direction, minus z direction, and then, oops. So you put a hyperplane perpendicular to that, the z direction, and then move it as far as you can till you go to the end of the polytope. So that's sort of, it is an easy problem to solve. All that you do is, in a polytope, you just have to scan through all the points and see in that direction where is the extreme thing located, right? So you reach that point. That I call as s of minus z, which is usually referred as the contact function, which is basically given any direction. What s tries to do is that you go along the direction and pick the point that is farthest. Yes. Is okay now, Manik?
No.
Oh, okay.
I'm sorry.
You try coming again.
Describe what you're saying, that would help a lot.
Oh, okay. So there is a convex set, right? And then there is the origin, which is typically outside, and you're trying to find the point on that convex set closest to the origin. Okay? And then to do that, the Gilbert's algorithm, what it does, it starts with the point inside the convex set, and then connects that point to the origin, and then along that minus z direction, right? Z is my current point. So minus z direction, you try to move a hyperplane perpendicular to it until you go reach the last point which you can touch on the polytope, and call that as the contact point. Okay, that's the contact function. And now what you do is you join your original z with that contact point, s of minus z. You form a line segment, right? And then now on that line segment you find out which point is closest to the origin, right? And that will be your next point, right? So that's essentially what Gilbert's algorithm is. It's a very simple algorithm which really doesn't require any complex calculation, like nothing like solving a system of linear equations or nothing like that. It's just you can write a closed form expression for it. And then once you have a new point, you continue, right? Now, it's a nice algorithm with you can show convergence properties and so on. And one comment I want to make again, repeat this, is that SMO, SOR, SVM, light, dual coordinates, and all these methods sort of fit into this class of methods. The algorithm, the problem is that it doesn't have finite convergence, which it's sort of easy to guess. Even in the case of polytopes, right? You can even take a three-dimensional example like I've drawn. So basically what I've done is I've taken a plane on which I have thrown 4 points and formed the convex hull. So the convex hull sits on that plane, and then I have the origin which is outside that plane, and I'm trying to find the point in this convex hull closest to the origin, right? And so I start from some point z0, sorry, and I compute the contact point S of minus Z naught, join by line segment, find the closest point there, and then that becomes my new point, and then now I find the contact point corresponding to the minus Z1 direction, join that, find the best point, and then keep going like that, right? So it just keeps on, it comes closer and closer, it converges, but then no finite convergence. So Gilbert and one of his students, Barr, then went on to create this new algorithm called the Barr-Gilbert Algorithm, looking for finite convergence. And actually this has very close relationship with a method called chunking, right? It's very, very similar in spirit. Here what it does, typical iteration, the same problem. You start with, the main mantra here is, in each step you find the minimizer on the convex hull of the current working set of points. So what you carry along with you working set of points, and then you find the minimizer on those points. So let me explain. So start with one point, find the contact point S of minus 0, and then join the line segment, find the minimizer. Alright, now you find S of minus Z1. Okay? Now unlike Gilbert's method where you throw out everything and then now worry about the line connecting Z1 and S of minus Z1. That's what Gilbert's algorithm would do. But here what you do is that you keep this point Z1 which has been formed requires both Z0 and S of minus Z0 to represent it. So therefore keep these 2 points. And then what you do is you include the new point. Now you form the triangle. And then on that you ask the question which is the closest point from the origin, and that on that triangle you get a point Z2. Now you see that the Z2 doesn't require Z0 for its representation, and therefore you throw it out, right? And then now you compute the contact point S of minus Z2, and then you form the minimizer on the convex hull of those 3 points. That turns out to be the nearest point itself, and you're done. Okay. So it has finite convergence, right? It keeps building the size of the working set, right? Now let me come to the Wolfe algorithm. So there is a negative point about the Barr-Gilbert algorithm, which is you have to find at each iteration the point closest to a simplex, right? A convex hull of a small dimension, smaller dimension points than the original set may be, but then it still requires you to find a minimizer on a simplex, which could be irritating. So Wolfe algorithm gets you out of that. So here is the way Wolfe's algorithm works. Start from, the main mantra here is that you don't do convex hulls, but you always work with affine hulls, which is, affine hulls is easier because finding a minimizer on a plane, for example, is very easy. Right? It's a set of linear equations. Start with Z0. Find the contact point, the line segment, and now you find the minimizer on the line connecting S0 and minus S0, S of minus 0, right? Not on the line segment, just on the line. But here it turns out that minimizer turns out to lie in between in the line segment. So keep those 2 points, you're done with the first step. Now you find the contact point, form the triangle, and now find the minimizer on the plane forming those containing those 3 points, right? And that will lead to Z2 hat, and go on like that, right? And next step you're basically done. Okay? So let me make some comments on the 2.
Sorry, if the point is outside the convex set?
You're still not done because you don't have proof that that's a minimizer, right? So you keep continuing until you actually capture it.
Even if it's outside?
Even if it's outside, yeah. Right. So until you have a certificate that you actually have a proof that is a minimizer, you have to keep continuing the algorithm. So Barr-Gilbert is a bit awkward because simplex, Wolfe replaces it by affine hull problem, so it's much better. Both have finite dimensions. They can go up to dimension d plus 1. In practice, they give very similar performance, but Wolfe is preferred because of the simplicity of calculations. So most matrix-based SVM methods are variations of this. And Wolfe applied his method to solve pattern classification problems in the 70s in IBM. And all implementations, even though we talked about in that Z space, but you can carry it out all in terms of the multipliers beta and using only inner products. Okay, that's where it's all suitable to kernel method. Now the third class of method, finite Newton method, which is the primal method. You go back to your original primal objective function, which is half norm w square plus summation I max of 0 1 minus yi w xi square, right? And this is it is a differentiable objective function, but then it is sort of quadratic patches. Okay, it's a patchy objective function, and therefore you can't simply directly use a quadratic optimizer on it, right? So finite Newton method, what it does is you're currently at a point wt and see in that loss terms which ones are active, right? And you form that index at it, and now restrict yourself only to that index set. Now it is purely a quadratic function, right? This one, and find a minimizer which amounts to equation solving, and then that becomes your and then your new point wt plus 1 is the best point on the sorry, not line segment between wt and w hat. Okay, so you basically form the active set, form a quadratic minimizer, but that quadratic minimizer may go out of that active region, right? So now you basically on that line segment you find the minimizer, and you repeat. So and if it turns out that you have working with linear kernels, that means directly you're operating in the original feature space, and your data has sparsity, then that linear equation which you're trying to solve, try to bring in suitable techniques like conjugate gradient and so on to make advantage sparsity, right? So this is an important class of methods. So let's go into now the history starts, right? Let's talk from 1970s. So how am I doing in time? So half hour, okay. All right, so let's talk about 70s and 80s, right? The problem characteristics, I probably messed up my, most of the problems did not bring in kernels, so they operate with the original X. Small feature space, at most 1,000 features. Number of examples is medium size, 10 power 4. Pretty much mostly hard margin formulations, and therefore dimension of that optimization space is same as the original feature space.
Sorry, what is hard margin?
Hard margin is when you look at a particular example, then you force that example and require that be properly classified. You don't allow that example to fall on the wrong side and give a penalization on that.
So your optimization problems as you formulated, are they hard margin or what?
It's that applies both to hard margin and soft margin, but if it is soft margin, I have to pad it with those extra terms on the last terms, right? With the hard margin, those disappear, right? So it just becomes minimizing the norms w square over hard constraints, whereas with loss terms you will have finally it comes to this form, but then I have to do this padding of extra terms in the w in order to do that. Okay,
every example
has to be
or has to have a margin.
No, yeah, it has to have a margin, right? That's right, it has to have a margin. That's right.
Different margins for different examples, or
it's the same margin, yeah. Of course you can look at variations. And the data matrix is typically dense, right? These are the kinds of problems they looked at. And because of the small size of the problems, typically when solving linear equations like in Wolfe's method, you use Kolesky or QR decomposition. So this is, the cost analysis is the one that is more interesting. So let me compare Wolfe and Wolfe and Gilbert's method, right? So both methods have to do contact function, right? A contact function, what it requires is that you give a direction and then you evaluate all inner products with points and find which is the farthest, right? and therefore the calculation that requires order ND effort. And apart from that, in Gilbert's algorithm, for example, you would find a minimizer on a line segment, which is very trivial, order D effort at most. Whereas the Wolfe will require some linear equation solving, and it turns out that even though I should write order D cube, but then it turns out that since everything you do incrementally, for example, when you have the QR decomposition of a previous set, you add a new point, then you just do incremental calculations in order to do the linear equation solving for the new set of points, right? Because of that, typically the complexity there is order D square. And the difference is that, for one thing, Gilbert's is not finitely convergent, but even if you put some tolerance to stop, the number of iterations turns out to be much, much larger than order D, right? There's a bit of hand waving, but exact complexities are not established, but typically much larger than order D, whereas Wolfe's and Barr-Gilbert's algorithm typically in the order of D, right? And so it turns out that the product of these two terms dominate the contact function. Within one iteration, it's the contact function that is dominating the picture, and therefore these things don't matter much, whereas this one is dominating. Therefore, take the product. And so because of that, Wolfe is the better method. And if you look at Gilbert's method, the main thing to watch out here is that you do some work in order to get a new point, but then you don't do sufficiently large work to do the remaining part of the iteration. And therefore, the two are really not commensurate with each other, right? Whereas on the other hand, Wolfe, it is trying to do a lot more work here, in the process gaining on the number of iterations, okay? That is the big point. So Wolfe is a lot faster than Gilbert, and so that's, in fact, with Wolfe, you can even try to increase this extra effort that you put into the various iterations and try to increase it even further so that it matches this order ND, right? So you can do things like, instead of bringing just 1 point new, you can, for example, bring the 3 best points or 4 best points or even more, right? And include them into the iteration so that you have the possibility of increasing the extra effort without causing problems with these two, but in the process reducing the number of iterations, so you gain, right? How is the dependence on tolerance? Dependence on tolerance, yeah, that is a nice question. So there is a linear convergence that you can establish for Gilbert, and typically in most machine learning problems you tend to stop at a big tolerance. You don't have to really push it to very small tolerance limits, and therefore this one, even though it's high, it's not that bad. Yeah.
So won't Wolfe have problems in the sense that you are allowing the variable to go out on the physical side in some sense?
No. Wolfe, what it does is that if you, let's say 3 points are there, right? And on the affine hull you find a point.
Right.
Let's say it's outside.
Right.
You connect that to the previous point. And then see where it hits this set, and that will be the next point, and so on, right? So it will always remain.
Sorry, this is the question I was asking.
Yeah.
You don't take the point outside.
No. Yeah. So what I was commenting, I sort of missed that. Yeah. What I was commenting was that outside point you found in that example, it actually is the nearest point, but then you didn't have a certificate for it, right? And
the nearest point inside the convex hull, right? What do you mean?
No. So you have 4 points, right? You worked with 3 points, and when you took the affine hull and you found a point, that actually is in the convex hull of the 4 points, but then you don't know about it at this stage, right? Because you haven't come to that. So now you join it to the previous point and see where it hits the convex hull of 3 points, and that will be a new point. But if you continue, the next step, it actually captures that point right inside. Okay?
So you bring it back to the convex hull of the current set of test points.
Right.
Because the overall convex hull you have to do a linear program to check. That's too costly, right?
Yeah, if you want to check, it will be expensive. Yeah, that's right. You don't have to do that. It just the algorithm does it. Okay, so So this is the story here. So the Wolfe is the better method here, right? So one of the things that I will come to before I finish the talk is that you see a wave going on. The Wolfe will look very good now, but then just a couple of slides later it looked bad, right? So, and each method keeps coming back again and again, right? We are not done with the story. So then we did apply to robust Hopfield Net Design, which I want to mention quickly. So in Hopfield networks, you have you use a dynamic update formula. ST plus 1 is the signum function applied on a matrix W times ST. Okay, and therefore you are basically applying a linear operation on a pattern ST, and then you apply a signum function, you get the new pattern, and then you keep repeating that, right? It's a recursive process, and you start from some starting point, and it converges finally to some pattern S star, right? And so we say that the starting point S naught has been detected to be this pattern S star. Okay, that's what we say, right? So the aim of Hopfield net is the user comes in and says, hey, here is a collection of S stars, particular, for example, images of the characters A to Z, right? And I want to store them in this Hopfield net, okay, with noise. So in other words, I give these patterns as the central patterns, but then you give a noisy version of them. I want the Hopfield network to go and converge to the correct pattern, right? That's what this is all about. And we want, so essentially, noisy versions of S naught to be detected as S star. And so one formulation of this noisy version, the robust formulation is, you take one S star, let's say, and then look at all patterns S naught which are at a Hamming distance less than or equal to capital R, and require that every one of these patterns converges to S star through the Hopfield network dynamics. Okay? And we want to make this capital R as large as possible, right? And obviously you cannot make extremely big because you are trying to, the other patterns also have a region of attraction, and therefore at some point there will be interference. Therefore determining the maximum R is an interesting problem, which is what we are trying to solve. So our algorithm is basically fix R and then look for a finding of a weight vector W that will do that, and then try the bigger R and so on, right? And try to find the max R that way. And you can convert this into our nearest point problem as follows. The thing is that you are requiring S naught to converge to S star through the Hopfield process, and that is a series of nonlinear operations, and therefore that is complex to deal with, and therefore the problem is simplified by requiring that in one step we require that these noisy points converge to S star, right? So this is a simpler convex way of expressing the robust requirement, okay? So instead of saying that the full dynamics will converge to S star, we require that these noisy patterns right in one step have to converge, right? So that simplifies the problem. And so to show that it's a nice convex problem, take one component of S, okay, and look at the jth row of that weight matrix W, and so you can basically put one step convergence requirement as a bunch of inequalities, okay, linear inequalities in W. And the complex thing is that has to hold for every noisy point S which is in that region of attraction, the Hamming distance region, okay, and that set can be very large, right? So that makes it a bit nasty. But so you write it as a hard margin problem by putting putting a margin on this and then minimizing the norm Wj square, right? So that becomes a problem which fits into our framework. And it turns out that very much like column generation ideas in linear programming, it turns out that even though this set B is large, right, because it's a Hamming sphere centered around S star, the calculation of the contact function can be done in pretty speedy time. Right? All that you need to do is do one sorting operation and pick up the most negative ones and then switch their signs. Okay? That's an easy problem to solve. And because of that, the whole thing is very tractable. And it turns out that determination of each row of W is all decoupled, and therefore you can solve separately. And so the dimension we are talking about is one particular row of W, Wj, and so that has dimension same as the original feature space. So this is the dimension of the optimization space. And now do a cost analysis, and what you find is that the contact function, like we said, is a d log d operation we talked about, and you're doing for every one of the patterns, and therefore the n comes in, say n d log d. And the other costs on the iterations are very similar for Gilbert and like before. Okay, there's no change in that. And again, very similar to what I talked about earlier, Wolfe is again a lot faster because of that. You're doing much more work in Wolfe per iteration, and the process decreasing the number of iterations. Okay. So next we move to SVMs, kernel SVMs, right? So in fact, my history is that I come from all this background, been solving those problems, and then when I saw the first paper on SVMs, I said, I'll try Wolfe's method. I know Wolfe's method is very good from my background, so that's the first one I attempted, right? And what I'll be showing here is that that is not really the right method because of the characteristics here. So what we have here is we have a nonlinear map. And even though the feature space is small, the example space is large, and the transformed space is inaccessible, right? In the sense that if you take RBF kernel, it sits in an infinite dimensional space, so you have to access it through all inner products, right? And so all computations are done via inner products, and support vectors, you define them to be those which are active in the final solution. In other words, those which have the non-negative betas. And let me assume in the worst case to do the analysis that the number of support vectors in a typical problem is also very large. It's in the order of n, right? And which is typically the case when you use squared hinge laws, actually. And even though you have this F factor coming in, one can actually, doesn't have to, worry about that issue, because it turns out that when you have n examples, right, in the feature space, in the transform feature space, these are going to lie in subspace of dimension n at most, and therefore you can, for all practical purpose of analysis, you can take d equal to n, okay, which is what I'll use. So what happens here? So you'll talk about large problems, and you have to work with the kernel matrix, all inner products, and that kernel matrix is n by n. So I'm going to assume that n is very large of this size, and therefore storing the entire kernel matrix is ruled out. And therefore you cannot do anything of the Cholesky QR kind of operations in Wolfe. That's ruled out. And if you look at the contact function, in fact this is a special situation of the contact function which I have written here, is that now you can actually rewrite the contact function in terms of all kernel functions, which is not difficult to see. But so you typically operate by storing this k times beta as a vector v, and then keep updating it as iterations move on. Okay, and the nice thing is that if it turns out that, for example, in a particular iteration only one beta changes, then the updating of the v turns out to be very efficient. You just have to form one column of the kernel matrix in order to do the updates, right? And therefore its cost is order n. Okay, this turns out to be crucial. On the other hand, if you change every beta, then you need the entire kernel matrix in order to do the updating of the required vector v. Okay? And so these are conditions very suited for Gilbert's algorithm and all its relatives. Okay? We'll do the analysis. So what we have is, if you look at, if you're thinking of changing, let's say, I'm writing it in a slightly general form in the sense that look at an algorithm which, like for example, SVM Lite, which modifies k betas in one iteration, right? Not the Gilbert's algorithm, modifies, brings in only one new point, so k is equal to 1. But a slightly complex version may bring in bring in more points and update them, and so k betas are changing, and therefore, you have this these various updates here, and so if you look at the other costs in the iteration, right, which corresponds to the updating of that vector v I was talking about. If you modify only k betas, then order kn is the complexity, but then if you end up touching every one of the betas, let's say at least in that order, it will be order n square, which is the bad thing. Okay? That is what kills Wolfe. And if you look at Gilbert's algorithm, the contact function and the other costs are sort of nicely commensurate with each other. Particularly, let's say if you put k equal to 1, the two are very close to each other in terms of order, whereas on the other hand, these two are very far from being commensurate, right? And therefore, even though in this method you gain in terms of the number of iterations, because this is very nicely commensurate with each other, Gilbert algorithm, in spite of the number of iterations being larger, turns out to be the better method. Okay? And effect of increasing k, the number of points you work with in each iteration, instead of just one point like in Gilbert, you can bring in more points. What happens is that your other costs go up as you increase k, but then that will bring down the number of iterations. So it depends on how much gain each one is leading to. So typically it happens that in most problems you can adjust k, and typically that k is a small number, like between 1 to 20. That's the order that gives you the best performance. It depends on the data set. And so till date, for this kind of situation where the entire kernel matrix cannot be loaded into memory, these Gilbert type algorithms, right, turn out to be the best for nonlinear kernel methods. And so now we have actually gone into a wave, right? You went from a case where Wolfe's method was very good, and then you went to a case where the Gilbert type algorithms are better. Now you come back, linear SVMs. So you are solving large scale problems, linear SVM problems in, let's say, web mining, text classification, etc., where the number of examples is large, number of features is large, right? So D is in the, and then you directly solve the problem in that space. And the original data matrix, it itself leads to Z, and therefore these data points are directly accessible to you. You don't have to worry about any kernels. And typically in these kinds of problems, that data matrix also turns out to be sparse, right? For example, an average number of words in one example is only 100, right? And storing is not a problem. Any linear equation can be solved using conjugate gradients. And so it turns out that Wolfe, the Barr-Gilbert types turn out to be better than Gilbert method for the dual solution. But even better is that the third class of method, which is directly solving the primal, right? The finite Newton method I was talking about. So again, let's talk about the cost analysis. So I start with a nonlinear case. Okay, I'm just repeating that slide for the nonlinear case, where we found that the Wolfe was not suitable because the entire kernel matrix has to be brought in each iteration. That made it really bad. Now when we move into linear, suddenly this computation becomes very, very simple now, because you take the direct data matrix and then operate on it. Those are the points for you, right? And therefore that turns out to be much simpler. And Gilbert also improves, but then now you see this disconnect between the contact function and the other costs, right? So Gilbert is doing a lot of work in the contact function, but at the same time is not doing as much here, whereas these two are very nicely commensurate with each other, right? And so Gilbert loses out on the number of iterations because the contact function is the one that's going to dominate, and therefore the method that has lesser number of iterations gains, right? So primal solution, it turns out to be the best actually. It's pretty much an order n kind of solver. Now this, whatever I've shown before in the talk about linear SVM, but it turns out that some of those apply to even nonlinear situations. When you deal with polynomial kernels with small degrees, you may be better off just expanding out those features and then transforming it into a linear problem and then operating in that space, right? Now again the cycle repeats, right? You come back. The next class of methods, right? Here a new set of problem characteristics. The training sets, let's say, are very huge, very big, like in click modeling where data is automatically collected. You're talking about in the order of 10 power 8 examples which are available to you. And typically this is the key here, which is that this n usually is much larger than the point where the learning curve stabilizes. So you may require, let's say, only around 10 power 7 points for the learning curve to start stabilizing, but then your data set is actually much bigger, right? And that's the kind of situation I'm talking about here. And also if the data turns out to be streamed, then you would like to make quick progress as and when data arrives. You would like to make improvements, right? So from these viewpoints, now if you look at methods like stochastic gradient descent methods, right? Stochastic gradient descent basically looks at an example, computes that partial gradient based on that example, and then makes a step, right? And that kind of method is very suitable for this kind of situation. And if you look at the batch primal methods, right? The finite gradient, finite Newton kind of methods which I talked about, they require the entire data for one step. Even to just compute one gradient, they have to make an entire pass through the whole data, right? And therefore they are slow because they need to wait for the entire set of points to make any even simple small progress. On the other hand, the stochastic gradient descent method, for example, would have already gone quite a bit by finding excellent weight vectors by that time, right? So coming back to the cost analysis, so we said that this is the earlier slide where we said that the Gilbert's algorithm, these two are not commensurate with each other. Now in this new thing, what we do is instead of doing this order n here in the contact function, which is required to make a sweep of all the points and pick the point that is the worst, right? Now what you do is that you use an online approach, and as soon as an example arrives, if it is in the improving direction, go ahead and make a step. You don't do a full round of all the points, and therefore that also becomes order 1, right? And therefore now suddenly these two become commensurate. And even though the number of iteration increases, but not bad, and also there is a continuous progress right from the beginning, right? And so in the process, the example-wise gradient type methods, that is, you look at one example at a time and then make immediate progress, right? That kind of approach makes them actually very, very suitable for a solution for this kind of problems, right? And now you go one more level, right? So it's ups and downs, and it's again continuous, right? So you go into let's say Terascale data, where examples again add clicks and splice site recognition kinds of, you're in the order of billions of examples and features, you're in that space. And so again, linear solvers, but distributed solution suddenly becomes essential. And now what happens is that you're back to the primal solvers, the primal finite gradient methods, finite Newton methods. Example wise, Gilbert type methods are not suitable because they're essentially sequential in nature, right? And whereas the primal, the gradient based methods like finite Newton, even though they operate with batch, now that you can distribute the data and then do it fast, suddenly they become the better ones, right? And so the battle continues between these two classes, the three classes of methods, right? And so closing comments is that different instantiations of the same three groups of methods have shown to be efficient in different scenarios. And who knows, in the future you'll come across more scenarios, a different version of these methods will come back. But again, it's again, you're coming back to same methods again and again. We are not really inventing any new methods, but it's working with the same three methods. And so you really, when you're faced with a particular problem and you want to use this class of methods, you really have to look at commensurateness of the complexity especially within iteration. And if you do that right, you will have typically a very good method. Right? So that's pretty much it. Right? So any questions? Just about that. Yeah, go ahead, Mani.
So, this is something that you probably didn't touch on in your talk, but there are lots of people here who know stochastic gradient descent very well, and you've come up with this dual coordinate descent linear.
Right.
I just wanted you to contrast them, because when I go and implement these things, to me it seems that the dual coordinate descent has three major advantages. One is that you're working with actual gradients rather than subgradients. The second is you take an optimal step in your line search rather than creating a fiddly parameter in stochastic gradient descent. Third is that you can maintain an active set in the dual.
Correct.
So can you just comment on these and what you think are these important?
Yeah. So like you said, the biggest advantage is that, of course, stochastic gradient, stochastic descent methods are acting on the primal, and dual coordinate descent is working on the dual, right? And therefore they're really two different things. Also, although the calculations look pretty similar, there is always an attraction for primal methods, because if you typically draw as time progresses the progress in the objective function on the dual as well as the primal, the dual, if it keeps on increasing towards its dual optimality value, right? And if you correspondingly plot what happens in the primal, and that will be very jumpy up and down, right? Although we know that it will finally converge, it has that up and down behavior, right? And therefore they give a sort of a non-smooth feel on the primal, especially in the early stages, right? So that is one, right away I want to mention one negative point about the DCD methods, okay? Because they are operating on the dual. But then the advantage is that in the case of stochastic descent of DCD, because as they, that they are increasing the dual objective function, but then if you go and correspondingly plot the primal, that will be jumpy. Stochastic descent will fluctuate because of its looking at only one example. But what I'm saying is it may not be as bad as what the jumps you see in dual coordinate descent.
I just want to make one comment here.
Yeah,
I don't know if this connection is very well known, but dual coordinate descent is the same as implicit updates in the primal. So if you do stochastic gradient descent and you do implicit updates, then they are the same. They are one and the same.
So what do you mean by implicit updates?
Implicit updates are basically the way you motivate the online learning updates is by saying you want to stay close to your previous parameter and then you want to minimize your loss. If you solve this equation exactly, then it turns out those updates are implicit updates. But you cannot do that exactly, because usually what happens is you get a WT plus 1 and a gradient at WT
T plus 1, correct.
And
that's what he meant by implicit. Okay, got it. Okay, yeah, that's a nice point. Yeah.
Yeah.
So anyway,
Not
that's
all that different. I mean, at least in the first pass through the data,
right.
actually they're not all that different.
Yeah.
The second pass onwards things start.
True, but then the advantage DCD has is that because the objective function, that it is continuously improving and so on, right? So there is a clear convergence rates and all that you can establish, right? Whereas with stochastic gradient you don't have that. The end convergence rates turn out to be much better for dual coordinate descent compared to stochastic descent methods, right? So if you really plot towards the end how fast the objective function moves towards optimal, it's just you'll see a huge difference there, right? Because the stochastic descent methods don't even have a linear rate of convergence, right? You struggle to even reach that, whereas these ones have a definite linear rate of convergence and pretty good too. Only thing is, theoretically, the point, so there is a slight catch for theoreticians, is that there is a point at which the linear convergence theory for dual coordinate descent starts, right? Because what happens is, as there is the constraint set, right? The alphas lying between limits. So there is always a jumpiness, right? And there is a certain point in time in the dual coordinate descent after which it will not change that set anymore, right? It'll, like if some alpha remains positive, it will remain positive for the rest of the journey, right? And so once it reaches that stage, that's where the linear convergence arguments kick off, right? But when you reach that stage, people have no answers for that. There's no theoretical answers. So theoretically speaking, the stochastic descent people always come back and say, hey, you don't know how, when you're going to reach that, right? So there is a little bit of gap. But practically speaking, I think dual coordinate descents are the ones I would go for. In fact, we had detailed discussions with the Pegasus guys, for example, and they do agree that DCD is the right way to go for, from a practical point of view.